In this video, we're going to be applying the ideas of polarity that we discussed in the previous lesson to help us understand what actually holds substances together. And that is what we call intermolecular forces, which is commonly abbreviated IMFs. So these are the attractions between molecules. We know that we know that matter exists as molecules. So for instance, a glass of water has millions and millions and millions of water molecules in that glass. And in order for them to stay in that glass, to stay as a liquid, there must be something holding them together. And that is the intermolecular forces. So these are attractive forces between separate molecules. That hold substances together. So a few things to keep in mind. First and foremost, intermolecular forces are not bonds. When two molecules are attracted by an intermolecular force, they're not connected chemically, they're just kind of attracted to one another. So I like to think of intermolecular forces as kind of like Velcro, whereas bonds are more like super glue. That it's a chemical bond is a much more permanent connection between two atoms, that if you break a bond, that is a chemical change. That is a chemical reaction. Your substance is not the same substance anymore. But breaking an intermolecular force is just pulling two things apart. That you had two water molecules that were stuck together, and now you have two water molecules that aren't stuck together, but they're still water, and it's much easier to pull those apart. You know, Velcro, you can just kind of stick and unstick as you want to, but once you have superglued two things together, it's really hard to get them back apart. You can do it. You can dissolve superglue if you have the right solvents, but it's a chemical change to undo that connection. So intermolecular forces are not the same as bonds, and in fact, they are much, much weaker than bonds. And again, breaking a bond changes the identity of the chemical. Breaking an IMF does not. So, different types of substances contain different types of intermolecular forces, and this is where the polarity thing is going to come into play, because intermolecular forces have an effect on a whole bunch of different properties that we're going to talk about a few of in the next video. So we want to be able to identify what types of intermolecular forces are present in a substance to help us understand something about its properties, or to be able to predict something about its properties. So there are three major types of intermolecular forces that we're going to talk about. The first are known as London dispersion forces. Or sometimes these are called van der Waals forces. Either name is fine with me. So these are present in everything. You can have more than one type. Some substances just have London dispersion. Some substances have dispersion plus other things that we will get to in a moment. So if you were asked to list all of the intermolecular forces present in a substance, London dispersion should definitely be on your list because it is in everything. So regardless of polarity, London dispersion forces will always be present in a substance. And what these are, simplest description, is that these are an attraction between what we can refer to as temporary dipoles. So in the previous video, we talked about polar molecules, or identifying polar molecules, and we said that a polar molecule is also known as a dipole. We would call those a permanent dipole, something that always has a separation of charge. Temporary dipoles occur because a molecule is a big cloud of electrons, and at some particular moment in time, just statistically speaking, there are probably a few more electrons on one side than the other, just because they're constantly flying around. That odds are good that at any given moment they're going to be a little bit off balance, creating a little bit of temporary separation of charge just for that one moment in time. So everything can and will have temporary dipoles, at least some of the time. So this is just a momentary uneven distribution in electrons. And that in a molecule, and that causes an attraction between those two molecules, that the partially negatively charged end of one molecule is going to be attracted to the partially positively charged end of another molecule. So because of the sort of temporary nature of London dispersion forces, that your electrons are shifting back and forth, your dipoles are there only for like a tiny fraction of a second, and then it shifts and the dipole goes in the other direction, that usually makes these the weakest type of intermolecular force. But these get stronger as the molecule gets larger. And actually can become quite strong compared to the other types of intermolecular forces that we'll talk about in a minute. Still nowhere near approaching the strength of a covalent or ionic bond. But they can become quite strong for large molecules. So just be aware that usually these are on the weaker side. If you're comparing molecules of similar size, these are going to be the weakest of the types of intermolecular forces that we'll talk about. But if you're comparing molecules of very different sizes, then that can become a factor, that the larger one is going to have stronger London dispersion forces because of that increase in size. And the reason why size matters is just that there's more electrons. In a larger molecule, you have a bigger electron cloud, so it's more likely that it's going to be a little bit off balance just because you have more electrons present. So our next type of intermolecular force is known as dipole-dipole interactions, or dipole-dipole forces. Is an attraction between polar molecules. So this is present in all polar substances. And it is an attraction between permanent dipoles. So for instance, if we have something like HCl, This is a polar molecule because we have two atoms connected together that are not equal in electronegativity. The chlorine is more electronegative, so it's going to have a little bit of negative charge. The hydrogen is less electronegative, so it will have a little bit of positive charge. And so what is going to happen if we think of this as, if we think of this as an electron cloud, the electrons are spending more time near the chlorine. It's sort of got this lopsided shape to it, where we have a negative end over here and a little bit of a positive end over here. So the way these molecules are going to line up is in such a way as to maximize the attractive forces. They're still moving around, but on average, you're going to find that you end up with the positive end of one molecule oriented towards the negative end of another. Actually, just move these onto the next page so I have a little bit more space. So we can see that we have this idea of opposites attract once again. So the negative end of one molecule is attracted to the positive end of another. And so that is the attraction that's happening with a dipole-dipole interaction that is holding these substances together, that is holding polar substances together. So because of the because of the permanent nature of the dipoles in polar substances, these tend to be a little bit stronger than London dispersion forces, usually, again, not always. But if you're comparing molecules of similar size, then the dipole-dipole is probably going to be the stronger of the two. So usually stronger than London dispersion for molecules of similar size. And then last but not least, we have one more type of intermolecular force, which is known as hydrogen bonding. So, first and foremost, yes, it's called hydrogen bonding. No, it is not a bond. I think every chemistry teacher in existence probably hates the name hydrogen bonding because it reinforces a misconception, which is the opposite of what we're trying to do here. So yes, it's called hydrogen bonding. No, it is not a bond. It is an intermolecular force, which is not the same. So just reinforcing that. So hydrogen bonding is present in polar molecules that have a specific structural feature, or one of a few anyways. So polar molecules that contain either a nitrogen-hydrogen bond, an oxygen-hydrogen bond, or a fluorine-hydrogen bond. So the reason for this is that these bonds are very highly polar. That in each of these, the hydrogen has a partial positive charge, and whatever it is connected to has a partial negative charge, and it's a pretty significant charge. So hydrogen bonding is really just a stronger type of dipole-dipole force. So it's really the same thing as a dipole-dipole interaction, just when that interaction involves one of these bonds, it tends to be stronger, so we call it something different. We call it hydrogen bonding. So what happens in hydrogen bonding is a partially positively charged hydrogen in one molecule is attracted to a partially negatively charged NO or F in another. So the most familiar substance that undergoes hydrogen bonding is water. If we look at a water molecule, we have oxygen-hydrogen bonds. So we have a slight negative charge on the oxygen. We have slight positive charges on both of our hydrogens. So this means that multiple water molecules can interact in such a way as to create a hydrogen bond between them. So the hydrogen bond would be this connection, this attraction right here. Note that I am not drawing it like a bond. Bonds in these types of structures are indicated as a line. This is not a bond, so you should not draw a hydrogen bond as a line. There is no official way to draw a hydrogen bond because it's not something that we usually really draw. But if you wanted to represent it in a diagram, any kind of dotted line, dashed line is fine. Basically anything other than a straight solid line, because a straight solid line means a covalent bond, and a hydrogen bond is not a covalent bond. It is the attraction between two separate molecules where it's a hydrogen on one molecule attracted to oxygen, nitrogen, or fluorine on the other. So hydrogen bonding does tend to be the strongest of the three intermolecular forces that we've talked about. Again, comparing things of similar size is important there. So it's like dipole-dipole, but a little stronger. So these different intermolecular forces, which ones are present, how strong they are, has a big effect on the properties of a lot of different substances, on all substances really. And we'll explore those in some more depth in the next lesson.